Welcome, everybody. This is the Rotary E-Club of Silicon Valley, and every week we work to bring you stories of people who are making a difference in the lives of others, improving their communities locally, globally, and digitally. And today we're going to talk energy. So our speaker today is Kemp Gregory, the CEO and co-founder of Renewell Energy. And when we talk about issues related to energy, there are a number of questions that often don't get enough attention, and these guys have come up with a beautiful way of addressing one of them. And so we're quite excited to get that story. So Kemp, with that, I hand the mic over to you. Welcome to the Rotary E-Club of Silicon Valley.
Great, thanks very much. Nice to be here. I am excited to talk about what Renewell, my early stage startup, is up to. And in the process, going to look forward to the questions and answers that will come from the crowd, and see if we can't make some progress in this little world so that we can reflect greater progress without. Okay, all right, so what I'm going to talk a bit today to y'all about is converting idle wells into gravity-based energy storage. The concept of a battery continues to expand as all sorts of different technologies are coming into the battery world. We are an entrant into the battery world, except we are strictly mechanical. So I'll explain the system in full detail later, but really there's a lot of poetic justice here in that what we're doing is we're taking idle oil and gas infrastructure, which is worth, like, not an exaggeration to say, trillions of dollars, and turning it into the infrastructure that's going to help us build the future. So a little bit about myself, how I got to this position. I'm originally from Houston, Texas. I went to UT Austin for mechanical engineering, then I went to go work for Shell as a completions engineer for 5 years. So I was a petroleum engineer, West Texas, Canada, and Argentina. And I was actually living in Argentina working for Shell, and I decided I don't want to work for Shell anymore. I don't want to work in the oil and gas industry anymore. I want to do something else. I want to go into the electricity side of things. So then I went to Stanford to get a master's in civil environmental engineering. And that's where this idea was born. It was sort of a divine combination of everything that I was at Stanford to learn, plus a lot of the things that I learned from my years at Shell. Okay, without further ado, let's talk about the problem. Okay, the problem is that the idle well count in the United States and Canada is enormous. It's 2.6 million wells, the vast majority of which are in the United States. And it is an expensive and slow process. It would take about 100 years to clean them all up in a business as usual scenario, $182 billion, and we're going to leak a lot of methane in the process if we keep doing what we're doing. So really, we're here to talk about two problems, actually. The other problem is that wind and solar, although their prices come down extraordinarily, and that's great for lots of reasons, we are faced with the inexorable challenge of matching Mother Nature's supply curve to civilization's demand curve. Neither are willing to budge, so what we've got to do is create some energy storage that can move things around, specifically move supply around. And so that, as a society, we have turned to the lithium-ion battery, which has been very, very useful, but it faces some challenges in doing this, solving this problem at scale. Those problems are, it's high cost. It's usually only applied for short duration, and by that I mean, tops out at the 4 to 8 hour range. But we're going to need some more like 50 hours worth of coverage in certain scenarios. It degrades over time, and there's an environmental impact, all of which I'll touch on a little bit later. So the way we solve the first problem is called plug and abandonment. This is an industry term. I didn't make it up. It just means that the well goes from being a liability to being nothing. But a little bit of context is key here. So when I talk about an idle well, I'm talking about something that has three distinct characteristics. It is not plugged, so it's just sitting there open to the reservoir. It is not an orphan well, so it is still owned by someone, usually a big company, and it has not produced oil and gas in the last 2 years. So it's sitting there truly just doing nothing. And they're often on top of depleted reservoirs. So even if oil price went to $500 per barrel tomorrow, it's not like all the idle wells will just go away. We're talking about a relatively permanent liability. But every oil and gas company is required to clean up every single well they own, and that's where the plug and abandonment comes in. And I'm going to walk you through what that process looks like quickly. So you take the pump jack away, you take the electrical infrastructure away, you take the tubing out of the well, you put 3 plugs in it. If we're in California, other states have different rulings, but it's typically about this. You cut the wellhead off and you make it whatever it was, forest if it was forest, desert if it was desert, you get the idea. The thing is, that's expensive. It's on average 70 grand and can be way higher, up to 5 times higher than that. Well, not, there are averages that are up to 5 times higher than that. There are wells that cost $1 million to plug and abandon. All that said, about 20,000 happen every year, but it's not something the oil and gas company industry is really that excited about. They don't want to do it because it costs money and they don't make any money in the process. So the other solution that we've turned to for the other problem, the renewable energy problem, is lithium-ion batteries. So here's some stack ups of various battery technologies and their 2030 capital cost. And here's how we compare against them. So we can have extraordinarily low capital costs for 2 reasons. One, we're repurposing a bunch of infrastructure, so we don't have to pay for that much. And 2, we actually have 2 revenue streams. One, there's the energy storage services that we provide to the grid, like any other battery. And then there's another one where we are helping the oil and gas company convert their idle wells into gravity wells, and we charge them for that. That's a service. And so in doing so, that well gets to get pulled off of death row, if you will, and given a whole new life. And then the oil and gas company basically turns into a little landlord. We pay them rent for the well, but we charge them an upfront fee for the conversion process. Okay, so for every time that we, extract more lithium out of the ground, at least in a hard rock example, we're talking about a massive mine versus an oil well cleanup. The price of lithium carbonate has gone up 7 times over the last 2 years. It's gone up by 7 times over the last 2 years. Versus us, we'll just use waste streams, used oil field tubing, and sand, anything cheap that we can put inside the well, the weight that goes into the wellbore. And lithium-ion batteries degrade up to 40% over a 20-year lifetime, whereas we have 0 degradation because we're strictly a mechanical system. So without further ado, I'm going to tell you a little bit more about how our system works. So the better solution to both of those problems is energy storage plus plug and monitor. So we're going to increase the environmental compliance and create the most flexible energy storage in the world. So we start by taking the pump jack away, leave the electrical infrastructure, because that's super important, take the tubing out, put a plug in the well, and now we install our system. So we call this system a gravity well. It is a mechatronic energy conversion, or just another way to say a fancy regenerative winch. It has a motor generator, kind of like a Tesla has a motor generator. So when the weight is moving down the well, we're pushing power to the grid. And when the weight is moving up the well, we're pulling power from the grid to motor. So it's weight moving up means we're motoring, weight moving down means we're generating. So it's power in, power out. Then we add a few more gizmos to this, specifically a MT style pack off and a trip tank to do fluid chemistry sampling, methane gas detection, and fluid volume monitoring. And the pack off is there just in case of the freak occurrence of there being pressure in the well. We can seal it up, make sure there's no leaks. So just to reiterate, totally mechanical system. It just works by converting potential energy to kinetic energy to electrical energy back and forth. Okay, so how it works, a well needs to be deemed suitable. All right, so it's got to meet 9 criteria for whether or not the well is a good candidate for conversion into a gravity well. So let's say that this well on the left here has passed all the tests and it meets all the criteria. So what would happen is a workover rig, which is like a shrunken drilling rig, would go out and do the first few steps of plug and abandonment. The same steps we just walked through, actually. So the pump jack goes away, and the tubing gets taken out, and the plug gets under the bottom of the well. And then we use that same workover rig, the shrunken drilling rig, to install our weights. And then we set our system down next to it, and it's ready to go. So what's happening there is that finally, it'll serve for 30 years as an energy storage mechanism. So performing things like load shifting, electricity arbitrage, and frequency regulation, lots of things that other batteries do. And I'll get to sort of the unique application of our battery in just a few slides. So we field tested this. We did it in Texas. There's a beautiful well that we found in Texas and then repurposed, and we're going to get to see a few videos and images of that. There's the workover rig. There's us moving in our prototype, which we call Artemis Prime. And here it is operating. So a little tour, you can see briefly that the drum is spinning counterclockwise, which means we're pushing power to the grid, or we're in that generating mode, which means the weight is moving down the well. Then we packed it up and we shipped it out to California. So here's us in a field owned by Energy. So we picked up the system, set it down, and now it's operating in California. The reason being is that I think California is the beachhead market. Lots of good things going on in California for this process. So technology advantages, just a little bit of summary and some more information. So I mentioned how we seal the wells, so the well won't leak any more methane. Even if it does, we would be able to monitor it and know. So in that effect, what we've essentially created is a net negative CO2 equivalent energy storage technology. We will stop more methane from leaking out of the well in its CO2 equivalent quantity than is the equivalent amount of energy and its CO2 equivalent emissions required to build the device. So like the embodied carbon versus the amount of carbon we're going to prevent from hitting the atmosphere in the form of methane, this is significantly more. So for every device, we're actually reducing the amount of CO2, not adding. And then the round trip efficiency is something that we established in the Texas pilot. We have a range. We topped out at 74%, which is actually a little bit higher than we were expecting as our top end. But if we can get to 80%, which is where we expect to be, then we will essentially be operating in the top tier of round trip efficiencies compared to other energy storage technologies. Last but not least, this is the most fun. All right, so what we've done that's truly innovative is combine gravity-based energy storage and a distributed energy resource. So that's DER. And what we've done is we basically created a situation where we can do short and long duration and short and long term. Most energy storage technologies are going after short term or long duration. We can do it all. We can do 10 hours, we can do 100 hours, we can do 1 hour. And that's because we won't ever ask the weight to move at a significantly different speed, but we will combine different wells in clusters to operate in different output scenarios. So you could have 10 wells operate perfectly simultaneously. To be a 1 hour discharge, it takes about an hour to get from top to bottom. And then it takes about an hour to get from bottom to top. So you could recharge all that system in 1 hour, recharge, right? Not electrochemically. But then you could have all those wells, all 10 wells operate perfectly sequentially. And it would be effectively a 10-hour battery. And it can do anywhere in between 6.7, 5.2, you get the idea. So that makes us extraordinarily unique, and we think that in the future, it's the most flexible energy storage technology that will win, because what the grid is going to need is not going to be discrete and arbitrary amounts of duration. It's going to be weather dependent, which is going to be variable. So one day the grid's going to need 50 hours, the next day it's going to need 212, and the next day it's going to need 91.7. It's just going to be variable. So the technology that can match that is going to have an intrinsic advantage. This is just to give you some scale. So there are 284 gigawatt hours of energy storage capacity in the United States today. That's dominated by hydroelectric, pumped hydro, but we're not building any more of those. And what you're looking at today is on this map is the wind and solar footprint. And what it needs to be by 2050 is significantly more, just a dramatic amount more wind and solar. And we're going to need 1,300 gigawatt hours of energy storage to make that happen. So now I'm going to lay the wells on top of this. And we think that we could have about 132 gigawatt hours of potential capacity by 2050. Now, this is not very much time, but it's a fun stat. We could power the entire United States for 20 minutes at that scale. And so what we're talking about is converting upwards of 1 million idle wells. And that's sort of our North Star, our guiding principle, convert 1 million wells. So one more little note on this, on our environmental impact. A lot of people talk about, well, how much carbon are you actually removing? And so I mentioned that we remove it in a unique way, which is that we seal up the wells, prevent methane from leaking, but also wanted to quantify our energy storage impact. So that's what we call indirect, and then sealing up the wells is what we call direct. So base load displacement, this is just assuming coal's on the margin. We can displace that many tons of CO2 a year, and it comes out to about 350 million tons by 2050. And that's just the United States. There's another million or so odd wells in the rest of the world. that could have a pretty important impact as well. And last but not least, we really want the impact. Like I said, we want to plug a lot of wells, right? This is a volume play. We want to have a significant impact on the cleanup process. And that's why we made the company. And so here you can see like a us versus business as usual scenario. And we really just want to blow it out of the water. We want for way more wells to get cleaned up way faster and turned into energy storage much faster than they would have just simply been filled full of cement and buried. That's it. Happy to take questions, and thanks for this platform.
Fantastic, Kemp. Thank you very much. It is wonderful to hear about what certainly looks to be a win-win-win situation. And I'd like to get to the Q&A. Let me introduce the people we've got on the West Coast, and including our speaker, Kemp. We have me, all right, the programs chair. We also have our paella master, Shags Chagrin in Walnut Creek. And over on the East Coast, we have Cal Mann, one of our members who has a lot of great experience on the Peace Corps as well. So Cal, Shags, good to have you guys on. Let's start with a question from Cal. Cal, go ahead and unmute and ask your question.
Sure, thanks. Interesting presentation. Your slides showed the little electrical grid. It looked exactly the same in all the slides. I am not an expert on wells, but I've seen a lot of them, and I don't recall seeing electrical infrastructure there. So can you tell me about like how much variation is there in the electrical grid connection in those oil wells? And then I guess the question would be, how much connection do you need to build out to that? Because without the distribution of electricity back to the grid, the whole thing is just a weight going up and down, correct?
Yeah, right. So we need there to be the presence of electrical infrastructure. We need it to be right up to the wellhead. Fortunately, that's often the case, particularly in mature oil fields. But even in new ones, especially for fracked wells, because they need a pump jack sooner than later. Usually they only flow for about 6 to 9 months on their own. But the reason I brought this image back up again is because we get this question all the time. It's a good question, Cal. And so this is a picture of the field that we've installed our pilot in. And so I want to go through a little mental exercise here, or a visual exercise. I want you to try to spot as many pump jacks as you possibly can. And there's a lot. I mean, just sort of straight down the image, you sort of lose count. Then now I want you to look for something else. I want you to look for the little black vertical lines. And those are all poles. And you can't see the wires because they're too thin. But in some places, if you look closely, you actually can. But this is an enormous amount of electrical infrastructure built up into this field. And places like Texas, Oklahoma, Kansas, New Mexico, places where it's dominated by oil production, and North Dakota, you're going to see this type of electrical infrastructure in there because they don't want to have to pay diesel prices to run a generator that powers their pump check. They want to pay electricity prices. And so the funny thing is the oil and gas companies have paid like an arm and a leg to build out these electrical infrastructures over the last 70 years as our wells have become less and less prolific and needing more and more help from the surface, i.e. pump jacks and whatever else. So if a well is truly out there in the middle of nowhere, Cal, then we just don't consider it. Fortunately, it's a numbers game. So there, like I said, there's 2.6 million. We only assume, we only expect there to be about a third of the wells will be suitable. For various reasons. There's 9 criteria that we evaluate a wellbore by. Electrical infrastructure is one of them. So we don't assume every well is convertible, but we think that even 30%, talking about hundreds of thousands of wells of just today's idle well stock. That's the 2.6 million. There's another couple million active wells out there that will eventually be inactive. That's how we get to the idea of being able to convert 1 million wells.
Very cool. And with regard to connecting to the grid, are there any issues related to distance that you had to overcome in making the case for doing this? So I not being an electrical engineer or a petroleum engineer, I'm kind of in the, this is really interesting, right? But I'm in California, and there's lots of things happening in California. it's all close enough to make a difference for me, I assume. But is it such that the grid works, that if you had loads and loads and loads of idle wells converted in the middle of the country, that would benefit farther areas?
Yeah, the short-term answer is that a lot of people think that you got to be close to a city in order to help from an energy storage standpoint. And from a grid operator perspective, that's not necessarily true. You do want to be close to demand, right? You need to be close to demand. And often people just equate demand to cities, which is, not wrong. It's right. But these oil fields are still active, which means they consume an enormous amount of power. And they are our demand. They are our load that we're helping in the same way that we would help an urban area with its load. So we're kind of like, we are embedded inside of an active oil and gas field using lots of power, and we're helping the grid by better managing the oil field and its electrical demand. Now, one day, like if we ever, made this come to pass and the mass, like all of Kansas is basically one gravity-based energy storage battery, one, that would be amazing. And two, what I don't show here is, it's actually pretty interesting. There are 3 grids in the United States, really. There's a West Coast one that more or less meets in the middle of the country. There's East Coast one that more or less meets in the middle of the country. And then there's a Texas grid. And so we couldn't have really planned it better. And that if we converted all of those wells in the middle of the country, you're sort of talking about a battery, a massive battery right in the middle of the country. And so it would be able to help a lot with sort of load balancing across those 2 grids. But even still, look at the sheer number of wells in like Pennsylvania and Ohio. You're sort of embedded within large population centers there too. So if we get to that problem where it's like, hey, how far, like we have so much storage, how can we get it to where we need it to go? Then something will have gone extremely right. But yeah, the short term is that we'll be embedded inside active oil fields. Let's say those oil fields stop making oil, like we really have a peak demand world and oil demand starts trickling down, then we would just start helping the grid, even if we were a little far away from it, because there's still tons of transmission constraints that are happening, even not like just between cities, that we could be helpful on. Plus, a lot of this map's communication is trying to tell you that having energy storage near supply is just as important as having energy storage near demand. So being able to soak up the wind right next to the wind and then push it back onto the grid whenever it's more valuable is sort of status quo, because the wind is sort of far away from the demand centers also.
So you mentioned during the presentation that California represents a good place to be doing these things. What are the conditions in California that make this? Is it just the high demand? Is it something different?
Yeah, it more or less falls into 3 categories. One, the oil and gas industry in California is bizarrely consolidated. So 65% of all idle oil and gas wells are owned by 3 companies in California. That's California Resources Corporation, Chevron, and Era Energy. You're not going to find that anywhere else. Even in Texas, which has 10x more idle wells, it's way more distributed amongst way more players. So California, basically, it was the opportunity to knock on 3 doors and get to something like 24,000 inactive wells instead of the inverse proportions, 24,000 wells to get 3 wells, 24,000 doors to get to 3 wells apiece. So very consolidated oil and gas industry, sort of, and this is the oil and gas world is one of these buckets, and really, really high plug and abandonment costs. So the customer is feeling a large pain point, and that's great for us because then we can provide a solution that's still expensive, but still cheaper than whatever it is their other option is, which is plug and abandonment. So really good oil and gas conditions. Yeah. And the next bucket is like California's hungry for energy storage, very, very hungry. They've made really, really aggressive mandates for how much energy storage needs to go into the system. So that's exceptionally good. And then finally, regulatorily, they are, and I mean specifically their oil and gas regulator, is very on top of their game, very well managed, and we think the most likely to be receptive to something like this. Because we need a gravity well recognized, right? Anything in the oil field today it's got some sort of title. It's an injector well, it's a observer well, it's an active well, it's an inactive well, it's any kind of, we're not on that list for obvious reasons. All we have is a prototype. But we've been really, really encouraged by the response we've gotten from the oil and gas regulator about having our system in the state.
Fantastic. Cal, you have another question.
You showed a slide that had the costs and you had lithium in there. I just want to understand, was that under the assumption that you're building and paying for a lithium battery for the sole purpose of storage and not in use with anything else? So for example, if you had a fleet of school buses that are sitting that are connected to the grid, not in use, that you paid for them for the purpose of those, operating those buses, but when they're idle, they could be used for storage.
Yeah, I'm not comparing myself to that. I'm comparing the technology to buying lithium-ion batteries in large quantities, putting them in a big farm, if you will, and then using those strictly for utility scale energy storage.
So one more question before we wind down, and that has to do with the business itself. So, it seems like you have brought together these different pieces. You have a compelling pitch to make. How is it at this stage in your work, having moved from being a petroleum engineer to being a guy who's kind of into this, that how is it going that you look at fundraising and how you attract investors into something like this?
Yeah, we've had a very fortunate 2022 where we've basically reeled in about $3.1 million in grants. That's really dominated by a $2.7 million grant from ARPA-E, which is like Obama made ARPA-E to be like the energy equivalent to DARPA. And so that's been really great, plus some other money from the DOE. And we've also raised $3.1 million, just sort of coincidentally, same number, from our seed round. So we've been very blessed with some funds that are going to help us build this business. And there's a little bit of room left in the seed round. If anybody listening is curious about that, I'd be happy to reach out or respond to reach out. You should hopefully have my email there at the end. Perfect.
All right. So in a minute, I'll hand it back to you for a final word, but let's do the standard wind down. First of all, thank you everyone for joining us. It is very much our goal that we connect with these people who have these wonderfully interesting stories that inspire us to think about solutions to vexing problems in all sorts of ways. This is a feature of what Rotary is. Rotary International, 1.4 million Rotarians and Rotaractors and 36,000 plus clubs around the world dedicated to making their communities better. And so it is a pleasure as the Rotary E-Club of Silicon Valley, which you can find at rotary.cool, of course, and let us know what you think, right? So after you finish watching this video, if you're watching it on YouTube, just note that there's a link to our site a little farther down. If you're watching it on our SiliconValleyRotary.com site on one of our meeting pages, scroll down a little bit, you'll find an attendance section, and you can let us know you were here. That's great for us to just kind of get a sense of what kind of reach we have. And then a little farther down at the bottom of the page, you'll find the forum, the discuss section, DISQUS, where you can leave thoughts about what you saw in this presentation and other elements of the meeting as well. You can respond to other people's comments. We encourage people to get in and share ideas in a wonderfully kind and productive way. So with that, we appreciate that you're being part of this today. And as we like to do, we hand it back to our speaker for the final word. So Kemp, what would you like for people to be thinking about as they walk away from the recording?
Just know that what Renewell is building is the lowest cost, highest GHG abating, most flexible energy storage in the world.
Beautifully succinct. Great. Everyone, we will see you next week.